Hey everybody. Today we're talking about variability and bias in statistics. The big goal of statistical inference is to use sample data to draw conclusions about populations. Typically, we estimate a population parameter using a sample statistic. For instance, if we go out and get a poll of 1,200 voters and find that candidate A leads candidate B by 8 points, the point is that we're expecting candidate A to win the election by 8 points. That's our best guess at that. Now, of course, we don't expect that to be exactly right. If candidate A ends up winning the election by 7.8 percentage points, no one's surprised. But if we don't expect our estimates, our statistics, to be exactly right all the time, then how do we actually distinguish between a good one and a bad one? This next definition is super relevant to that. A statistic p hat is said to be unbiased if it's equal to the corresponding parameter p on average. So in the example we're talking about, the p hat is the 8 percentage points by which candidate A leads candidate B in the poll, and p, the parameter, is the amount by which candidate A actually wins the election, if in fact they actually win. So the result of any one sample might be high or low, sometimes by a lot, but neither direction is favored. And if the study's done repeatedly, like if we do that poll over and over again, the average value of all the various p hats should just be p. If we average all the statistics, we get the actual parameter. One really important warning here is that we're using the word bias in a technical sense, whether the statistic agrees with the parameter on average. We're not specifically talking about prejudice and discrimination. We're talking about the bias of the statistic, not the researcher. Obviously, a biased researcher can be a cause of statistical bias. That's an important thing to talk about, but that's not specifically what this definition is referring to. Some common sources of bias in sample surveys. The big one is sample bias, where not all members of the population are equally likely to be selected in a random sample. Like in a telephone poll, for instance, when we're talking about politics, if you're not including cell phones, you're going to miss out on a lot of potential voters. A more serious problem is just that people don't tend to answer their phones from unknown numbers. Sampling bias is a little bit of an umbrella term. It captures a lot of different, more specific sorts of bias, including non-response bias. Those that refuse to participate in the survey can be different in relevant ways from those that do not refuse. So potentially candidate A's voters are more likely to answer that poll than candidate B's, and that can absolutely cause a biased statistic. Another one to watch out for is asymmetric questions or other non-neutral language, and these can incline respondents to answer in a certain way. Closely related is social desirability bias, where respondents are less likely to give answers that are viewed as socially unacceptable, particularly when their anonymity isn't guaranteed or if they're talking to a live interviewer. A lot of the potential sources of bias in observational studies are also potentially present in experiments, but I want to mention a couple other potential sources of bias that are a bit more specific to experiments. The big one here is lack of control. If experimental groups differ in relevant ways beyond just the treatment being applied, the results of the experiment may be biased. Here, there's potential for the presence of confounding variables. Another potential source of bias is lack of blinding. Ideally, neither the experimenter nor the subjects should know which experimental group they're in, or who's in which experimental group. If they do, that can change the results. It can be a form of lack of control, and that can bias the study. Another extremely important one is the lack of randomization. Assigning treatment groups without using random assignment can lead to non-uniformity. We want the treatment groups to be as similar as possible, except for the treatment being applied, and one of the ways we accomplish that is through the randomization process. So if you're not doing that, you can expect lack of control and therefore bias. Now, even an unbiased statistic is unlikely to agree with a parameter exactly. For instance, in that poll, if we have an 8-point margin in the poll and the actual margin in the election is 7.8 points, we're not surprised, like I said earlier. The term for this is variability, and that's just the tendency of a statistic, in this case the margin that we got in the poll, to take different values just by random chance. Each particular random sample chosen for a study is probably going to lead to a different statistic, even if the sampling method is unbiased. So in that political poll, we go out, we do the poll again. We're not going to get 8 points every time. Sometimes it'll be a little higher, sometimes it'll be a little lower. That's variability. It's essential to remember that variability is not a form of bias. Samples seldom perfectly reflect the populations from which they're drawn, and even a high-quality poll, for instance, is likely to miss the mark slightly. Bias means that the results miss on average. Variability just means the results are different from one another. I think this picture is very helpful. The main thing as you're interpreting it is to think of each one of the points in each one of these 4 plots as a sample statistic. So for instance, in that poll, we've gone out, we've gotten a p hat, then we've done it again, one for each one of these dots. So I've drawn pictures that look like bullseyes. And so ideally, when we get a statistic, we want it to perfectly match up with the parameter. That would be hitting the bullseye. And if we miss, that's being further away from the center of the bullseye. So in the upper left, we have a situation where our statistic has both low bias and low variability. If we go out and get the statistic over and over and over again, we always get results that are near the actual parameter, and they are pretty tightly packed. On the upper right, we have high variability but low bias. On average, we're hitting the bullseye. Sort of if you take the centroid of all those points, you're right at the bullseye. But there's a lot more spread. There's a lot more variability from study to study. On the lower left, we have high bias but low variability. The statistics are all clustered very closely together, which seems great, but they're far away from the target, from the actual parameter. And on the lower right, we have high bias, high variability, so lots of spread, and on average, we're missing. And in certain ways, that seems like the worst case scenario. We'd prefer to have both low bias and low variability. Do notice, however, in that lower right plot that one of those statistics has actually hit the bullseye. So this is a situation where the high variability has kind of balanced out the high bias. And you will see this reported in the media sometimes. So-and-so was the only pollster that got the election right last time when everybody else missed. Well, maybe they're using very poor methodology to the point where this has happened. And they were just the one company that kind of got lucky in that situation.